What's up, Algebros and Broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, welcome. Today we're going to take a look at matrix operations in our course so that we can start talking about matrices. So we have a theorem to start with. Let A, B, and C be matrices of the same size, so same number of rows, same number of columns, and let R and S be scalars. And we have the following properties. First, matrix A plus matrix B is the same as matrix B plus matrix A. Right, so we get this nice commutativity property. Second, if we add A and B together first, and then add C to that result, that would be the same as adding B and C together first, and then adding A to that result. So we get a nice associativity property. We have A plus 0, 0 meaning the zero matrix. So I'm not going to be able to take a matrix and then just add a scalar to it. That operation doesn't even make sense. Whoops, where'd I go? Right here. That's my vanishing act. I won't ever do that again. This refers to A plus 0 equals A. 0 refers to the zero matrix. There's a matrix with all zeros in it, so we have an additive identity. Some distributive properties. If I have A and B and I'm adding them together, but I should be multiplying them by a scalar R, well, what I could do is I could distribute first. I could do R times matrix A plus R times matrix B, so a left distributive law. Here, if I'm summing scalars, R plus S, and that should be times matrix A, I have a right distributive law where I can do R times A plus S times A. And then just regrouping coefficients. If I have R times quantity S times matrix A, I could actually group those scalars together and say, well, that's R times S and then times matrix A. We got a definition. Oh yeah. If A is an M by N matrix and B is an N by P matrix, where B has columns little b sub 1, little b sub 2, little b sub 3, so on and so forth to little b sub P, then the product of A times B is the M by P matrix whose columns are A times B sub 1, A times B sub 2, A times B sub 3, so on and so forth, A times B sub P. And then here we have some symbolic way of writing that A times B is equal to matrix A times, this is matrix B, but I'm writing it out in terms of its columns. B sub 1 is a column, B sub 2 is a column, B sub 3 is a column, so on and so forth. B sub P is a column. When we think about multiplying think about sort of distributing. We're showing how we can build the columns of that product. When we say each column of A times B is a linear combination of the columns of A using weights from the corresponding column of B. And some important information in here is the idea that if I'm multiplying A times B, and I'm thinking about the sizes, we said A is an M by N matrix, and B is an N by P matrix. In order to multiply these together, I need these two sort of inner values to match up. So we'd say, well, the number of columns in matrix A and the number of rows in matrix B have to be the same. Since those two agree, they're both n in this case, then the size of the product that I'm going to get are coming from these outer pieces, right? So then the result would be of size m by p. It's just discussing sizes. So an m by n times an n by p is going to give me an m by p for the result. Let's talk about the row column rule as well, and this is what we're going to really want to focus on when it comes time to multiply matrices. We say if the product A times B is defined, then the entry in row I in column J of A times B is the sum of the products of corresponding entries from row I of A and column J of B. If capital AB sub ij denotes the ijth entry in AB, the product, and if A is an m by n matrix, then AB little I sub j is going to be a little a sub 1, 1, B sub 1j, plus here we have A sub, that's going to be I2, and then B sub 2j, plus so on and so forth, plus we have A sub in and then B sub nj. Now, this is a very textbook definition of this row column rule. I'm going to go through, we're going to see some examples, I'm going to discuss how to do this, and hopefully we can get a sense as to what the mechanics are. And I think after you do it enough times, it's going to be not a big deal at all. Row column rule, not too bad to do, but certainly describing it in a textbook manner can be a bit sort of scary looking, right? Let's take a look at some examples. Let's talk about our matrix operations. Here I have 4 matrices, A, B, C, and D, and I want to find these 3 things. I want B minus 2A, I want A times C, I want C times D. Let's start with B minus 2A. Now, you can think of this like subtraction, and I think it's natural to do that, but sometimes I like to think of subtracting like adding with negative coefficients. So I would think of B minus 2A as B plus a negative 2A. And you can judge me for that if you want to, but I think that this is a reasonable way to set this up. Because what I can actually do to start breaking this up into smaller tasks is I can first find negative 2 times matrix A. We can talk about how to do that. Well, what is matrix A? I have it given here. So I'll write it down and say, well, if I want to multiply this matrix by negative 2, how do we do that with matrices? Well, that means I want to multiply this coefficient into every single entry. Every single entry. So how is that going to look? Well, multiply everything by negative 2. So I'm going to get negative 4, and then 0, and then positive 2. And then second row, I'm going to get negative 8. Here I'm going to flip the sign and get positive 10. And then here I'm going to get negative 4. So not too bad multiplying a matrix by some scalar. But now I want B minus 2A, and I already found the minus 2A, so I want to add B to this minus 2A. So let's see what B was. B had entries, first row was 7, negative 5, 1. Second row was 1, negative 4, negative 3. And I want to add this to the negative 2A, which I just found. So I'm rewriting that. And then to add 2 matrices, and very important that they are the exact same size, I want to add corresponding entries together to get the result. So upper left corner, right, 7 plus negative 4 is going to give me 3. I can move over, negative 5 plus 0 is going to give me negative 5. And then here in the upper right corner, 1 plus 2 gives me positive 3. And I can do the same for that second row. So here bottom left, 1 plus negative 8 gives me negative 7. In the middle, negative 4 plus 10 gives me positive 6. And bottom right corner, negative 3 plus negative 4 gives me negative 7. So not too bad. So this is my B minus 2A that we found. This one right here. So okay, so far so good. Next I want A times C. So let's see, A times C. So what was matrix A? Matrix A was 2, 0, negative 1 for the first row. And what was it? 4, 5, 4, negative 5, 2. 4, negative 5, 2 for that second row. And then times matrix C. So I just want to write them next to each other first to think about how that multiplication is going to look. Matrix C was rows 1, 2, negative 2, 1. Okay. Now, before multiplying matrices together, it's not a bad idea, especially when starting, to get an idea as to what the size would be of that product. So here, if I go and I sort of write this out, remember it's always row and then column. How many rows do I have? I have 1, 2 rows by 1, 2, 3 columns. And I'm multiplying to this. What do I have for the size here? I have 2 rows and 2 columns. So I have 2 by 3 times, this is a 2 by 2, a square matrix actually. And right away we're going to notice an issue. What did we say earlier about the sizes? I need these to match up on the inside. I can have an m by n times an n by p because those two inner values match up. But in this case, that's not happening, right? 2 by 3 times a 3 by 2 by 3 times a 2 by 2, these don't match. which means that the product is not defined. So I'm not able to do A times C. Now we're going to take a look at the row-column rule next, but something interesting to consider, if I tried doing the row-column rule for this, it wouldn't make sense, because what that would entail is fixing this first row of matrix A and fixing the first column of matrix C and multiplying corresponding entries. I can do the first entries, I can do the second entries product, but there's not a third entry here for this first column of C. So at some point it doesn't make sense, right? I can start it, okay, and then okay, but then, well, it's missing. You say, well, it's missing, so how can I really continue that operation? You can't. I think the easiest way to see it is just by noting the sizes and that there's a discrepancy there that's not going to work out. Right? It's not going to work out. So, okay, so we can't find A times C, but important to know that. But what about C times D? So I am asked to find C times D. And let's write these ones out. So I can sort of cheat and look at matrix C here, head rows 1, 2, negative 2, 1. And then what about matrix D, head rows 3, 5, negative 1, 4. And first I can mention the size of the matrices. So these are both 2 by 2s. I have 2 rows, 2 columns, 2 rows, 2 columns, and a 2 by 2 times a 2 by 2. Since the inner values match up, they're both 2s, then the size of the product is going to be the outer values. And everything's a 2 here anyways, but it's the outer 2s that I'm using to tell me what the size of the product is. And this is nice because it helps me get an idea as to what that matrix should look like in terms of size, but I am going to draw it a bit exaggerated so that we can show how this row-column rule is going to work for multiplying. So what I want to do is I want to go to matrix C, the leftmost matrix, fix its first row, and then go to matrix D and fix its first column. So row-column rule. And I want to multiply corresponding entries, and I want to sum the products. So I want to multiply the first entries, so that's 1 times 3, and I can sort of write it out here, 1 times 3, and then plus, I want to multiply the second entries, that's 2 times negative 1. Now what I want to do next, let me actually get a little bit, maybe some more room here. I'll close the matrix in just a bit. But now I want to finish off this first row of my product matrix, I want to stay with the first row of C, but now I want to move to the second column of D. And I want to multiply in the same fashion. So the first entries are going to be 1 times 5. And second entries are going to be 2 times 4. Well, I'll do this in yellow, so I want to use the blue maybe for that. So it's 2 times 4. And let's get the yellow back. Always looks funny if you don't close your matrices. There it is. And now I want to build the second row of my product. So let's switch colors. So now what I do is I go back to matrix C, and now I want to fix the second row, but then I'm back to the first column of matrix D. And I multiply those corresponding entries together and sum the products. So first entry is negative 2 times 3, and then plus. Second entry is 1 times negative 1. And now for that last entry for my product, what I want to do is stick with this second row of C, but now I want to go to the second column of matrix D. We'll do negative 2 times 5. And then plus second entries 1 and 4. So plus 1 times 4. And this is just to show sort of the steps behind the scenes, but once we get really comfortable with this row column rule, we're going to be able to just probably do more of the arithmetic in our heads. But let's see what this result gives us. So here what do I get? I get 3 minus 2 is going to give me 1, 3 and negative 2. Here I have 5 and 8 is going to give me 13. Here I have a negative 6 and a negative 1 is going to give me negative 7. And here I have negative 10 plus 4 is going to give me negative 6. So this is C times D. Right? C times D. Now, we weren't asked to find this, but let's find D times C. Well, hold on a second. D should just be the same, right? C times D should be the same as D times C, right? Why wouldn't D times C be the exact same thing as C times D? Well, you know what? It's not. It's not going to be. So in general, we're used to this with just multiplying numbers, right? You say, okay, well, 15 times 9 is going to be the same as 9 times 15. That's fine with real numbers, but multiplying matrices, the order does matter. And let's actually see this so that we can kind of dispel this myth, right? It's not true. So if I reorder these, if I say, well, if matrix D is on the left, and that's 3, 5, negative 1, 4, and then matrix C to follow, 1, 2, negative 2, 1. If I multiply it out, is it going to give me the same thing? Well, I kind of already spoiled this and gave it away. We'll see that it's not going to. But let's go with our row column rule. Let me get the colors back if that helps. I want to fix this first row of matrix D and then the first column of matrix C. Multiply corresponding entries and add the products. And here I'm not going to write out everything, but I will write out the products. So I get first 3 times 1 gives me 3, plus 5 times negative 2 gives me negative 10. And then I'll figure that out later. But now I want to stick with this first row of D, but now I want to move to the second column of C. I get 3 times 2 gives me 6, plus 5 times 1 gives me 5. And then we'll do the second row of our product. So now I want to move down to the second row of D and to the first column of C. Multiply those corresponding entries, sum the products. Negative 1 times 1 gives me negative 1. 4 times negative 2 gives me negative 8. And I'm sticking with the second row of D, but now I'm going to have to move over to the second column of C. Negative 1 times 2 gives me negative 2. And 4 times 1 gives me 4. And this is what we wind up with. Let's go ahead and see if we can finish this off. See what this D times C matrix is all about. 3 minus 10 gives me negative 7. 6 plus 5 gives me 11. Negative 1 minus 8 gives me negative 9. And negative 2 plus 4 gives me positive 2. So this is what I get for D times C. But notice what we got for C times D and D times C are very dissimilar. Not at all the same. So I don't want to be thinking that they're the same. Let's take a look at some theorems and some general warnings to sort of talk about what we just talked about and a few other things to look out for. Theorem that we have, let A be an m by n matrix, and let B and C be matrices with sizes for which the indicated sums and products are defined. So if I'm going to be adding matrices, they have to be the same exact size. I'm going to be multiplying matrices, they have to be set up so that that product is defined. So just assuming that these things exist, we do have these properties. We have a nice associativity law of multiplication. If I do B and C multiplied together first and then multiply A times that, it'd be the same as if I want to multiply A and B together first and then multiply that to matrix C. So A times quantity B times C is the same as AB quantity times C. I have a left distributive law. So A times quantity B plus C, I can think of as A times B plus A times C. I have a right distributive law. If I have quantity B plus C and then times matrix A, I can think about multiplying in and getting B times A plus C times A. Remember, the order matters. And then here for a scalar, if I have R times and then quantity A times B, where R is a number and A and B are matrices, I could group this however I'd like. I could do R times matrix A and then times matrix B. Or I could do A times and then group scalar R times matrix B. And so maybe there's some advantage to bringing R into one of those matrices over the other. I have that opportunity. And then we have some identity matrices that we can talk about. But this gives us a multiplicative identity. I sub m, the m by m identity matrix times A, is equal to matrix A which is equal to A times I sub n, the n by n identity matrix. And we'll talk about what those identity matrices look like shortly in the lecture. But for now, just think of it as multiplying by a matrix that won't change, the matrix that we have, the identity matrix. Some warnings to consider. In general, A times B does not equal B times A. We just saw that. Could it happen? Sure. Is it likely to happen? No. Should I assume it's going to happen? No. Could it happen? Maybe. But is it going to happen? Probably not. Should I assume it's going to happen? No. Second, cancellation laws do not hold. That is, if A times B is equal to A times C, I can't conclude that B and C are the same, right? So I'm not going to be able to do anything like that, no sort of algebra that we're familiar with. And third, if the product of A and B gives us the zero matrix, we're not allowed to assume that either A is the zero matrix or B is the zero matrix. And here, A equals 0, B equals 0, this refers to the zero matrix. These are things that we're used to when working with, pre-calculus, algebra, stuff like that. It's not true for matrices, so be very careful with these properties. Well, sort of anti-properties. We don't get them. It's not true. False. So just be on the lookout for stuff like that. Let's take a look at an example. Here I'm given the matrix A, and I want to compute a couple of things. First, we want to compute A minus 5 times I sub 3. And I sub 3 refers to an identity matrix. Let's talk about identity matrices. I sub 3, an identity matrix is a square matrix. Same number of rows, same number of columns. So I sub 3 is a 3 by 3 matrix. And what the identity matrix is going to look like, it's going to have 1s on the main diagonal and 0s everywhere else. So this is I sub 3, the 3 by 3 identity matrix. It has rows 1, 0, 0, 0, 1, 0, 0, 0, 1. Just for the sake of seeing, a couple of others, we could have the 2 by 2 identity matrix, which is a 2 by 2 matrix with rows 1, 0, 0, 1. You could imagine then what the 4 by 4 identity matrix is going to look like. It's going to have rows 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Just 1s on the main diagonal, 0s everywhere else. This is our identity matrix. And if I multiply by the identity matrix, it's going to preserve what I have. But what I want to find first is A minus 5 times I sub 3. But what I could do, similar to what we did at the beginning of lecture, I could think of this like A plus negative 5 times I sub 3. And I could go ahead and find negative 5 times I sub 3. So I say, well, negative 5 times I sub 3 is negative 5 times this 3 by 3 identity matrix. And if I multiply this by negative 5, well, it's actually going to be a pretty quick result, if you notice, because whenever I multiply it to a 0, it's going to keep 0. Whenever I multiply it by a 1, it's just going to present that negative 5. So negative 5 times 1, and then I get 0, 0, and then here I get negative 5 times 0 is 0, but then negative 5 times 1 is negative 5, and then 0, and here I'm going to get, multiplying in, I'm going to get 0, 0, and then negative 5. But now what I want to do is I want to take matrix A and add to this. So I'm going to sort of jot down what matrix A was. So that had rows 5, negative 1, 3, negative 4, 3, negative 6, and then a last row, negative 3, 1, 2. And I want to add this to negative 5 I sub 3. You can subtract. I'm not saying don't subtract. You can subtract corresponding entries, but if it's all the same, I would think adding seems perfectly reasonable, adding with negative coefficients. And then here I would just want to go ahead and add these corresponding entries. So see what we get. 5 plus negative 5 gives me 0. Negative 1 plus 0 gives me negative 1. 3 plus 0 gives me 3. Move on to the second row. Negative 4 plus 0 gives me negative 4. 3 plus negative 5 gives me negative 2. Negative 6 plus 0 gives me negative 6. Third row, negative 3 plus 0 gives me negative 3. 1 plus 0 gives me 1. 2 plus negative 5 gives me negative 3. And this is what we get for, this was a minus 5 times I sub 3. This result right here. And there's one other thing for us to find here. Here we have grouped 5 times I sub 3 and then times a. Now, there's actually something nice that we can do with this. You can do the product as indicated, 5 times the identity matrix, and then times matrix A. We already did negative 5 times the identity matrix I sub 3. You can imagine what it would look like if I was multiplying a positive 5 to it. But we have a really nice property here to consider. This sort of a fourth property where if I have a scalar, then I can go ahead and sort of group it together. So I could think of this sort of like working at the middle here. This is my 5 I sub 3 times a, so to speak. And I can group this differently. So what I could do to consider is I could actually do the following. You could say, well, what if instead of doing it this way, if I think of this like 5 times, and then the identity matrix times matrix A. Now I have another property to help with this. So what did we just do? We just took advantage of this fourth property, sort of starting with the middle argument, and then I wrote it as this first argument. But now I can move down to the fifth property and say, well, if I have the identity matrix times matrix A, it's just going to give me matrix A. And I'll show that in just a moment. But so here we're saying the identity times A gives us A, so this is really 5 times matrix A. Well, what is that? Well, 5 times, let me write down what matrix A was again, since I already forgot. A had a first row, 5, negative 1, 3. Had a second row, negative 4, 3, negative 6. And had a third row, negative 3, 1, 2. And multiplying 5 to this just means multiplying every single entry by 5. And so this shouldn't be too bad. So 5 times 5 is 25, and then 5 times negative 1 is negative 5. 5 times 3 is 15. Moving to the second row, 5 times negative 4 is negative 20. 5 times 3 is 15. 5 times negative 6 is negative 30. 5 times negative 3 is negative 15. 5 times 1 is 5. And 5 times 2, lastly, is 10. So a quick way to get this result. Now, showing that the identity times A just gives us A back, we can do this. So I'll show it in the one direction, and then you can do it on your own in the other direction. But if I take my 3 by 3 identity matrix, and then multiply this on the left to matrix A, and what was that? Got it. Is that it? Did I remember it? Yes, looks good. If I go through my row column rule, let me get my product matrix here. Here I have a 3 by 3 times a 3 by 3, so the result is going to be a 3 by 3. Give me the blue. First row of the identity, first column of A, I'm going to get 1 times 5, 0 times negative 4, 0 times negative 3. So that's just going to give me 5 and then 0 and then 0, so I get 5. If I move over to that second column now, I get 1 times negative 1, 0 times 3, 0 times 1. So I get negative 1 and then 0 and then 0, so negative 1. And then moving to that third column, 1 times 3, and then 0 times negative 6, 0 times 2. So I get 3 and then 0 gives me 3. Now if I continue this process, and we'll just go through the rest of it since we're already here, I'll move now to the second row of the identity, and then to the first column of A, back to the first column of A. So here I get 0 times 5, 1 times negative 4, and 0 times negative 3. So 0, negative 4, 0 gives me negative 4. If I move to the second column of A, 0 times negative 1, 1 times 3, 0 times 1. So I get 0, 3, 0, so just 3 when I add them. And then now to the last column of A. So here I get 0 times 3, 1 times negative 6, 0 times 2. So it gives me 0, negative 6, and 0. Sums to give me negative 6. And then we'll just do one more is all we got. So now I'm going to go to the third row of the identity and back to the first column of A. We're going to get 0 times 5, 0 times negative 4, 1 times negative 3, which gives me negative 3. Now to the second column, 0 times negative 1, 0 times 3, 1 times 1 gives me 1. And now to the third column, 0 times 3, 0 times negative 6, 1 times 2 gives me 2. But notice what I got from this. I mean, just believe in the properties, right? Here we showed it, but it just gave me back matrix A, same matrix that I had. So the identity times matrix A, it is a multiplicative identity, just gives me matrix A back. But what we wanted to find was actually this. But here I'm just justifying to you that when I multiply by the identity, it does serve as that multiplicative identity. Let's talk a bit further about multiplying. Here I want to compute the product in two different ways. So here we have a definition that we talked about at the very beginning, where I can find A times little b sub 1 and A times little b sub 2, and then use that to construct columns of the product matrix A times B. But then we also have this row column rule for computing as well. And I want you to let me know in the comment section below which of these methods you actually prefer. But let's actually start with this first method, which has me finding A times little b sub 1 to start. So this would be matrix A. I'll just rewrite it. And then b sub 1 is the first column of B. Okay, so what do I want to do here? Well, we remember this. This is going to be our row vector rule for computing. And how we do this with the decomposition is we pick out this very first entry of the column vector and multiply it to this first column. So that would be 1 times 4, negative 3, 0. And then plus, now I pick out that second entry of the column vector, 3, and multiply that to this second column of A. And then I want to go through the operation here and I want to add them. So here we'll say, well, what is this going to give me? Well, here I get 4, negative 3, 0 times 1 is just going to stay 4, negative 3, 0. Plus, and then here multiplying by 3, I'm going to get negative 9. I'm going to get 15. I'm going to get 3. And then I can add these together to get a single vector. 4 plus negative 9 gives me negative 5. Negative 3 and 15 give me positive 12. And 0 plus 3 gives me 3. So this is A times b sub 1. And I want to do the same now for A times b sub 2. So I take matrix A, rewrite it again. But now the second column of B. So the second column, b sub 2, is 4 minus 2. But it's the same process. Now I'm going to pick these out one at a time and use them as weights on the columns. So this would be 4, the first entry of this column vector, times this first column of A. So 4 times in the column 4, negative 3, 0. And then plus, now I want to go to the second entry of that column vector, which is negative 2, and multiply that to the second column of A. The second column of A is negative 3, 5, 1. And we'd multiply these together. Multiply it out, right? We'll multiply it out, not together. 4 times 4 is 16. 4 times negative 3 is negative 12. 4 times 0 is 0. And then adding. Negative 2 times negative 3 gives me 6. Negative 2 times 5 gives me negative 10. And then negative 2 times 1 gives me negative 2. And then I can add these two vectors together. So 16 plus 6 gives me 22. Negative 12 plus negative 10 gives me negative 22. 0 plus negative 2 gives me negative 2. And this is A, B sub 2. Now to construct A times B, all we have to do is use these as columns of that product. So this first result I got for A, B sub 1, negative 5, 12, 3, that's going to be my first column. Negative 5, 12, 3. And A, B sub 2 is going to be my second column of the product. That's 22, negative 22, negative 2. Everything's looking great here. So that's how I can build this product. Now, if I don't want to be doing that, I can be using the row column rule. So this is just how we would define that product, but I don't think it's the best way to do this. So if I want A times B, then likely what we want to be doing, rewrite these. What was it? 4, negative 3, 0, and then negative 3, 5, 1 for the columns. And then matrix B. Matrix B was 1, 4, 3, negative 2. If I'm reading it off row-wise, 1, 4, 3, negative 2. So I got them rewritten. We can think about the sizes first. So row by column. So this is 3 rows, 2 columns. So a 3 by 2 times a 2 by 2. And since the innermost values match up, they're both 2's, the size of the product are going to be these outer values. So the product is going to be of size 3 by 2, which is actually the same size as A, if it helps to sort of consider that. And I can find this product. Now I want to use my row column rule. Let's get our colors. Blue. First row of A, first column of B, I get 4 times 1 is 4, plus negative 3 times 3 is negative 9. Now move to that second column of B. Sticking with this first row, 4 times 4 is 16, plus negative 3 times negative 2 is positive 6. Now we're going to go back to A. We're going to move to the second row, and to B, back to the first column. Negative 3 times 1 is negative 3. 5 times 3 is 15. And then now to the second column. Negative 3 times 4 is negative 12. 5 times negative 2 is negative 10. And then now we can go back to A, and now we're down to the third row. And then back in B to the first column. 0 times 1 is 0. 1 times 3 gives me 3. Now I can move, sticking with this third row, in B though, I can move to the second column. 0 times 4 is 0. 1 times negative 2 is negative 2. And now I can go ahead and finish the arithmetic to find this product matrix. 4 minus 9 gives me negative 5. 16 plus 6 gives me 22. Negative 3 and 5 gives me positive 12. Negative 12 and negative 10 give me negative 22. 0 and 3 give me 3 when I add them. 0 minus 2 gives me minus 2. So should look familiar, right? It's what I already got. It's not going to give me something different. It's just another way to compute it. But for me personally, I think this row column rule is very fast. Once we get comfortable with it, this is how we're going to want to be multiplying matrices. But if we're defining matrix multiplication, that isn't how we define it. It's just kind of a shortcut technique that we would use. We would define it with this sort of decomposed version. But very cool to think about how we can multiply these matrices together. Hey, let's take a look at some more. Speaking of multiplying matrices, let's do some more. Let's do A times D and D times A. Here, given these, go ahead and pause the video and try them out on your own and then rejoin me. A times D, let's start with it. You have a 3 by 3 times a 3 by 3. The result is going to give me a 3 by 3. I'm not going to worry with the colors, but we'll still go through all the mechanics of it. So first row, first column, 1 times 5, 2 times 0, 3 times 0. So I'm really just left with 5. If I move now to the second column, 1 times 0, 2 times 3, 3 times 0, I'm really just left with 6. And then now to this third column, but still in this first row, 1 times 0, 2 times 0, 3 times 2 is just going to give me 6. Now we're moving in A to the second row, but back to the first column. 2 times 5, 4 times 0, 5 times 0. So I'm really just left with 2 times 5, which is 10. Now moving to that second column of D, 2 times 0, 4 times 3, 5 times 0. So I'm really just left with 4 times 3, which is 12. Now moving to the third column of D, 2 times 0, 4 times 0, 5 times 2. So it's going to give me 10. Now I'm all the way down in A at the third row, but back to the first column of D, 3 times 5, 5 times 0, 6 times 0, so I'm left with 3 times 5, which is 15. Now to the second column of D, 3 times 0, 5 times 3, 6 times 0, so I'm left with 5 times 3 is 15. And then now third row still, but now third column, 3 times 0, 5 times 0, 6 times 2, so I'm left with 12. This is what I get for A times D. So you can see this row column rule can be relatively fast once you get feeling good about it. Let's do D times A. Here I can sort of cheat looking up here. D is 5, 0, 0, 0, 3, 0. I'm reading off the rows. 0, 0, 2. And then what about A was 1, 2, 3, 2, 4, 5, and 3, 5, 6. I can still kind of see it. And we know that the order that we multiply matrices matters, so A times D and D times A are not going to be the same necessarily, so we got to redo it. Do all the work. Well, not really redo it because they're not the same, but do it. We got to do it. Let's do our row column rule. So first row of D, first column of A, 5 times 1, 0 times 2, 0 times 3 gives me 5. And moving to that second column, 5 times 2, 0 times 4, 0 times 5 gives me 10. And then now last column, 5 times 3, 0 and 0, so it's just going to give me 15. Now I want to go to D and move to the second row, and then to the first column of A. 0 times 1, 3 times 2, 0 times 3 gives me 6. Now to the second column, 0 times 2, 3 times 4, 0 times 5, that's going to give me 12. Now to the last column, but sticking in this middle row of D, 0 times 3, 3 times 5, 0 times 6 is going to give me 15. Now I'm at the bottom row, third row of D, and then back to the first column of A though. 0 times 1, 0 times 2, 2 times 3 is just going to give me 6. Now at the second column of A, 0 times 2, 0 times 4, 2 times 5 gives me 10. And now third row by the third column, 0 times 3, 0 times 5, 2 times 6, so I'm just left with 12. So what I get for D times A is definitely different than what I got for A times D. There's something kind of interesting here, and I don't want you to assume this is always going to happen. It's not, but it has a lot to do with how, in particular, matrix D is constructed. Is notice that the rows and the columns have kind of interchanged. So this first row is 5, 6, 6, but here this first column is 5, 6, 6. The second row is 10, 12, 10. That's my second column here. The last column, the last row is 15, 15, 12, which is my last column here. Now that didn't happen before. If you remember when we did earlier on at the beginning, A times C and C times A, they were just completely different. There's something interesting happening here, which will segue us to our next conversation. I've got some extra room here for writing down some notes. You are the best. You know you are. You're doing a great job with the matrix multiplication. We're going to talk about transposes, is really what this is leading us to discover. An interesting topic. Given an m by n matrix A, the transpose of A is the n by m sized matrix denoted A transpose, and that's A for the matrix A, and then a superscript capital T for transpose. And to find this A transpose, whose columns are formed from the corresponding rows of A. So we're exchanging columns for rows and vice versa. We have some really interesting properties in this next theorem, though. Let A and B denote matrices whose sizes are appropriate for the following sums and products. A transpose transpose is the same as matrix A. If you think about it, we're exchanging columns for rows, and then again, it's just going to revert back to what it was. A really nice property for sums, if I have A plus B quantity and I want to transpose that, that's the same as A transpose plus B transpose. If I'm multiplying with scalars, let's say I want R times matrix A quantity, and I want to transpose that product, that's really the same as R times just A transpose. Because if you think about it, you can't really transpose a scalar. It's just a number, so there really is no transpose there. So RA transpose is the same as R times A transpose. But a very interesting property, and something that you definitely want to remember, and you don't want to just assume it's going to be the way you think it would be, is if I have a quantity, a product, A times B, and I want to transpose that, that would be the same as B transpose times A transpose. So notice the transpose of a product of matrices is the same as the product of their transposes, but in the reverse order. Right? I think we look at that and we think, well, shouldn't it be A transpose B transpose? No, it isn't. It's B transpose A transpose. So they switch order, and then we get that nice property. We're going to talk about transposes a lot throughout the course, but just to end off this lecture, let's take a look at a couple of examples. So here I'm given two vectors. I'm given a vector u with entries 5, negative 4, 2, and a vector v with entries x, y, z, and I want to compute u transpose times v and u times v transpose. Let's start with u transpose times v. So u transpose times v. How is this going to look? Well, to find u transpose, since this is a column vector, u transpose is really going to be a row vector. You think of it this way, my first row is 5, so my first column is going to be 5 in the transpose. My second row is negative 4, so my second column is going to be negative 4. And my third row is 2, so my last column is going to be 2. And then times v, so v is just going to stay the same, which is just a column vector x, y, z. But let's consider sizes here. What are the sizes? So here, u transpose, there's 1 row and 3 columns. So this is a 1 by 3 times, what about v? V has 1, 2, 3 rows, but 1 column. So the product exists, right? These middle values line up. They're both 3s. So the size of the resulting product is going to be these outer numbers. It's going to be a 1 by 1. Now, a 1 by 1 really isn't, or doesn't really need a matrix, right? It's just going to be one single entry. So in the spirit of that, I probably wouldn't want to put any bracket notation around it. That might sort of look misleading. It's just going to be one single entry. A 1 by 1 matrix is just one single thing in a box. So don't even really bother maybe putting it in the box. You can put it in the box if you want to, but I'm not going to because I don't want it to be misleading. We have row column rule. I'm not going to circle the row and the column because that's all I'd be circling is everything. So this is my row, this is my column. If I multiply corresponding entries, 5 times x gives me 5x, plus negative 4 times y is negative 4y, plus 2 times z gives me 2z. And this is that single entry. This is the one entry in my 1 by 1 matrix is 5x minus 4y plus 2z. That's it, the one entry. Very interesting. Well, what about this one? This will be our last one, u times v transpose. So now I want to take u as it was originally, and that was the column vector 5, negative 4, 2, times v transpose. In a similar way, v was a column vector x, y, z, so v transpose is going to be a row vector x, y, z. And I'd like to multiply these, but let's talk about the sizes. So here, u, 3 rows, 1 column, so this is a 3 by 1, times a 1 row, 3 columns, 1 by 3. So this is going to be drastically different. So here, 3 by 1 times a 1 by 3, the product exists, the 1 and the 1 match up. The size of the product is going to be a 3 by 3. And let's see what that 3 by 3 looks like. Let me sort of, I can do this down here on this last page. So first row, first column, let me get the new colors. this a bit bigger. We'll do the colors for this one. Let me know in the comments if you like doing the blue and the pink and the purple, or if you think, nah, I don't need to do it. First row of U, first column of V transpose. There's not really a lot to do here. In fact, I don't have to sum anything. It's just going to be multiplying those entries. 5 times x gives me 5x. Now, sticking with that first row, but moving to the second column of V transpose, 5 times y gives me 5y. And now to that third column, 5 times z gives me 5z. And then we went to the pink next. Now I'm going to go back to U and go to the second row, but back to the first column of V transpose. Negative 4 times x gives me negative 4x. Move to that second column, negative 4 times y gives me negative 4y. Move to that third column, negative 4 times z gives me negative 4z. It's kind of a funny looking negative 4, but I'll fix it. I don't want it to look like a mu. Negative 4z. And these are separate entries. I'm not stringing them. So it isn't negative 4x minus 4y minus 4z. It's negative 4x, pause, negative 4y, another entry, pause, perhaps a third entry, negative 4z in that second row. Now let's finish this off. So now I go to this third row of U and back to the first column of V transpose. It's going to be 2 times x gives me 2x. Move to that second column of V transpose. 2 times y gives me 2y. And you know what that last final entry is going to be. So staying in that third row of U and now the third column of V transpose. 2 times z gives me 2z. And this is that 3 by 3 matrix that we get for U times V transpose. This is U times V transpose. Okay. Hope you've enjoyed talking about these matrix operations as much as I have. No matter where you are and what you're doing, remember to always keep learning, keep dreaming, and follow your heart. We're going to be back at it with more math soon. Until then, make sure you take care of yourself, and I will see you next time.